So now we are at the module 4, basics of probability theory, right? So why this probability theory is important? The reason for reading this module is I wanted to introduce another loss function, that is binary cross entropy. And this binary cross entropy is one of the most fundamental and commonly used loss functions in deep learning or machine learning, right? So to understand that loss function well, we need to have some basic understanding about probability. Okay. Yeah. Fine. So I hope that probability theory you must have studied in your high school as well as as a part of your engineering mathematics, right? So I'll not go to the deep of it. I'll just introduce you the concept which is required for our scope. To start with, we'll start with one very well-established fact that a probability value can always lie between 0 and 1, right? It can never be negative and it cannot be more than 1. Now, the point number 2 says that if I'm having some event from 1 to n, right, and all those events are disjoint event, right, then the sum of union of those events is equal to the probability of union of those event is equal to sum of their individual event. Is this point clear, or shall I explain it? Right. Let me say that this is my sample space. Sample space, by the way, no? Sample space is the list of all possible outcome an experiment can give, right?
Okay.
Let's say that we perform some experiment and there are total n possible outcome that experiment can have. Okay. And all those outcomes are disjoint. For example, if the outcome is 1, then the outcome of 2 cannot happen. For example, tossing a coin, right? If you're tossing a coin, either you can have head or tail. If it is head, you won't get tail. If it is tail, you won't get head. It won't be a possible scenario when you're getting head and tail at the same time, unless your coin is biased. Okay. So this is my sample space, and this is my events, and all these events are disjoint event. Okay, these are my events. These are disjoint event. Now the probability of union of all this event. So here probability of event a1, comma a2 till an is equal to probability of a1 plus probability of a2 till probability of an. Okay. The third point says that the probability of universal set is always 1, right? For example, if you are tossing a coin, right, what is the probability that you will get either head or either tail? It is always 1, right? There is no other possible outcome you can have while tossing a coin. The possibility.
So, but why are you saying it's 1? Isn't it half?
No. I'm saying that if you're tossing a coin, what is the probability that you will get either head or tail?
Oh, it is 1 because you will get one of them.
Yes, that's why. That's why.
Okay.
Right.
Oh.
So the probability of universal set or the probability of sample space is always 1. Okay.
And the sample space means the whole thing.
Yes, all the possible outcome your experiment can have.
Okay, got it.
Okay. Is this 3 point clear to you?
Yeah.
Awesome. Okay. Can you quickly answer me this question if you've understood the previous slide? A container is filled with balls with 3 different colors, blue, green, red. If the probability of getting red ball is 1/4, what is the probability of getting either green or blue ball?
3/4.
Yep, 3/4. Which gives us the another formula which says that a probability of event A is X. Right? Then the probability of not happening that event X is 1. Sorry, 1 minus probability of X.
Yeah.
Right. Okay. Now this is really important. Now we're gonna approach the concept of random variable. Okay. So what is random variable? Let us see this with an example. Suppose a student gets one of the three possible grade, right? A student can only have one of the three possible grade, and that those are A, B, C. One way of interpreting this is that there is three possible event, right? Three possible event means, and first event that the student gets grade A, second event that the student gets grade B, and the third event the student gets grade C. Okay, this is a one way of interpreting it, right? The other way of interpreting it is, we can think of a function that maps student with different grades. Okay, so these are my student in a class, right? And each of the student will have some grade. It can be A, B, or C, right? So we can think here as a function, a G, which is mapping a student with some grade, right? So this function is nothing but a random variable. I know initially it can be a little bit confusing, though a random variable is a function, but it is called as a random variable, right?
So it's a function, right? But why we are calling it as random variable? It can be called as like a
Yeah, yeah, that's a perfectly valid question, but this is how the people have named it.
Okay.
Right? It's a function that maps your event with some number, but it is called a variable. To further reinforce this understanding, let me give another example. You're tossing a coin, right? There are two possible events you can have with respect to tossing a coin. What is your experiment here? Your experiment is tossing a coin. And what are the outcomes you can have or event? You can have head or tail, right? These are the two possible events. Okay, so what I say is I will denote my head by a number 0. I'll denote my tail by a number 1. Okay, so random variable is a function which is mapping your event to certain specific number. So here my random variable has mapped head with 0, tail with 1. Now I can write something like this, event. If I denote event by E, so E is equals to head, that is 0.5. Similarly, P is equals to E is equals to tail, that is also 0.5, right? Is this concept clear to you?
Yeah.
Okay.
But the above part was not like where you said that event is head is 0 and tail is 1. So why you're saying that head is 0 and tail is 1? What does that 0 and 1 are implying there?
It is just for our convention's sake. See, for example, if you are performing an experiment where you are having total 100 number of possible outcomes, right? You won't be remembering each of event by some by their respective outcome. Rather, it is easy to remember it by some code, some number 0, 1, 2, 3 till n, right?
Okay.
So, yeah, so it is just for our reference, just for coding sake, we have introduced this concept of random variable. Later you'll see how this is really simplifying the understanding when we are dealing with complex experiment.
So outcomes are being assigned a number. That's what you're saying.
Yes, outcomes will be assigned to number.
Okay.
Right. Any more question on this? No, right? Can you answer this? A random variable is just a mapping to a probabilistic event.
Yeah.
Yeah, the answer is true. Okay. All right. Now, moving ahead with the random variable. Okay. So if I have to define a random variable, I would say a random variable is a function which maps each outcome in omega to a value. Omega is the notation for sample space. Okay. So in the previous example, we saw that how my function, my random variable was mapped each of my student with some specific grade, right? Now this random variable can take two forms. One is called discrete random variable, another is called continuous random variable, right? So if you are performing an experiment where you know that the set of outcome you will be having is discrete in nature, for example, tossing a coin, right? This is an experiment which will give you a discrete random variable. The outcome will be either head or tail, right? Another example is maybe you have got a job to count the defective number of items from a conveyor belt. So here also your outcome will be always discrete, right? But now just think of an example or experiment where somebody has given you a task to measure the height of student of a class, right? So now your experiment can lead to continuous output. The height of a person can be anything. It is not to be discrete always.
So how are the two different? I mean, even though you have given two examples, but how is it one is discrete and one is continuous? Like what does it mean to be continuous and to be discrete?
Yeah. So it depends upon the experiment that you're performing and the type of output you're going to get from that experiment. If you're performing an experiment whose outcome is discrete, for example, tossing a coin, it can be either head or tail. It can be either
Yes.
0 or 1, right? Where 0 is my head and 1 is my tail, right? So this is my discrete random variable. Whereas if I have to measure a weight of some student, so the outcome could be anything, right? If you want to measure the weight of 5 student, the weight can be anything. It can be 60.1234. It can be 55 point any value. It can take any value, right? The outcome can take any value.
Yeah, so that means when the outcome is taking any value, we are saying it is a continuous random variable.
Yes, yes.
Right? And when the outcome is not taking any value, when it is in the form of, say, a binary form,
Yes,
this or that, then we're saying it is discrete.
yes,
So any
exactly.
scenario where you have this or that we will consider as discrete random variable. Otherwise, we will consider as a continuous random variable, right?
Yes, exactly.
Okay. Okay.
Here it is continuous, so continuous random variable, and this is discrete random variable. Okay, so these were the two types of random variable. Now answer this question.
So one question. So in the earlier slide, right, you gave these three scenarios: grades, height, and age, right? So grade is going to be discrete,
Yes,
right?
yes, this is going to be
Height and age
discrete.
are going to be continuous because it can be any value.
Yes, yep.
Okay.
It will be continuous. Similarly, age is also continuous random variable. Right?
But then why did you again classify it like short and tall, adult and young?
Yep.
As if you're making it binary, right? Why
Yes.
did you put that?
Yep. Yep. See, talking about the height, so height can be both. It can be continuous random variable also. It can be discrete random variable also. For example, if
Depending.
suppose, yeah, depending upon how you conceptualize it. For example, there is some notion set in your mind. For example, you say that if somebody is having height more than 150 centimeter, then you will consider him as tall. If the height is less than 150 centimeter, then you will consider it as a short. So now the same problem has become the problem of discrete random variable. But if you do not do this binning thing, then actually it's a problem of continuous.
Yeah, right. Okay, that makes sense.
Right. Similarly for age also. So age can be anything, right? If you want to take the literal age, your age can be like 30 years, 9 months, this much number of days, this much number of hours, this number of minutes and all. But how to but to simplify it, how people conceptualize it as, if suppose you are less than 18, you are a teenager or kid. it is something between 18 to 40, or it is youth. Beyond that, it is old age, like that. So it depends how you perceive the problem.
Okay. Yeah, I think it's absolutely clear now.
Okay. If it is clear, then quickly answer me this question. What is the relation between multi-class classification and probability? Mapping an input to a class can be considered as a random variable. Each class can be considered as a different random variable. We don't have relation in essence. For now, forget the question 1. This is something which you'll be able to answer after 2-3 slides. Focus on question 2. Which of these don't represents a continuous variable?
Grades.
Yes, you're correct. Okay. Now we have understood the concept of random variable. Now let us see the probability distribution. Okay, and this is important. And this is connected to random variable also. Okay. So what exactly we meant by saying a probability distributions? So let us take the same example. Let us take the example where we had 3 grades, A, B, and C. Okay. And we know the probability of getting a grade A, grade B, and grade C. Okay. So we can draw this table, right? We can come up with this table if we know the probability of student getting grade A, probability of student getting grade B, and probability of student getting grade C.
Yes.
Okay. This table is nothing, it is called probability distributions. It is consist of 2 things. One is the random variable itself. This is a random variable, right? This A is random variable, B is random variable, C is random variable. So on one side you will have the random variable, on the other side you will have the corresponding probability of occurrence of that particular random variable. That, so how do we read it is the probability of the experiment taking the random variable A is 0.1. The probability of experiment taking the outcome random variable B is 0.2. So this table is called mainly probability distributions. And you can represent this table in form of graph also. Right? So if I have to do it in graphical form, how would it look like? It would look like something like this. I'll have the x-axis, right? I'll have 3 things here, A, B, and C. A is what? 0.1. Then this is 0.2, B is, and C is my 0.7, which will have even more height. Okay. So if you know this table, you can come up with in a graphical form also, right? So this is the probability distribution. It is nothing, it is just consists of 2 columns. On one side, you'll have random variable. In the other side, you'll have their corresponding probability of occurrence. Okay. Right? Is it clear?
Yeah.
Okay. And now this probability distribution can take various shape, right? So for example, if I am tossing 2 coins together, right? Tossing a 2 coin. So what could be my possible outcome? My possible outcome could be I can get head, head. I can get head, tail. I can get tail, head. I can get tail, tail, right? So these are my random variables. Okay. These are my random variables of this experiment. And what would be my corresponding probability? 0.25, 0.25, right?
Yeah.
If I have to draw it in graph, it would look something like this. All will be at same height.
Yep.
right? This is called uniform probability distribution, right? Because the probability of each of my random variable is always same. Every random variable is having same probability value, right? This is called uniform probability distribution. Okay. We will see some more probability distributions later, but for now, I have introduced one kind of probability distribution, and that is uniform probability distribution.
So here, in the can you go to last slide? Yeah. So here you're saying specifying the marginal distribution over G means specifying G equal to G. Like what does that mean?
Yeah. So here P G equal to G. So G is what? Grade, right?
Yeah.
So this is a compact notation of this table, right? So here it says that the probability of my grade equal to G. So G can take any value, right? It can have A, B, or C.
Yeah.
Right. So this is a compact notation. This one line is a compact notation of this table, where my probability value can have either value A, B, or C, and these are my corresponding probability values. Okay. Yeah. The other name it is by what it is known is marginal distribution.
So probability distribution, other name is marginal distribution.
You can consider this probability distribution as a broad umbrella, right?
Okay.
And within that, what we have seen is the marginal distribution.
Okay. Got it.
Okay. Now, can you answer me this question? Sum of all marginal distribution gives limit of distribution should be greater than 1, gives probability density function is equal to 1.
Gives probability density function?
No, it is equal to 1. Yep, equal to 1.
Why 1?
Because see, this sum, the sum of all the possible outcome is always equal to sample space.
Yeah.
Right. And what is the probability of a sample space? It is always 1. Right.
Yeah.
So here also you can see that if I have to do the summation of all this, it is always equal to 1.
Yep.
Right. So that is why the sum of all marginal distribution is equal to 1.
Okay. Okay. Got it.
Now coming to the another thing that is called expected value of random variable. Okay. So what is expected value? Expected value is nothing but it is related to the average value, mean. Okay. But this is more defined for a distribution. Right. So for a discrete random variable, the expected value usually denoted by mu. This notation, it is nothing but it is expected value notation. Okay. And formula for expectation is this summation of xi f xi. Okay. I'll explain this formula. Yeah.
Yeah. So that, what do you call it? Mu. Okay. So mu and E of x, they mean same thing.
Yes. This E
right?
here means, yeah, this E means the expectation. X is my random variable. So expectation of my random variable, right?
Sure.
It is written, it is read as expectation of random variable X. Right?
Yeah.
And this random variable can take multiple values. For example, if I am tossing a coin 1,000 times, right? What is the, on an average, how many times I am likely to get head?
50% of the time.
Yes. The expectation of this is nothing but 50%. Right?
Yeah.
And the formula for this is summation of xi f xi. Okay. So let us do a small numerical to give you a complete feeling of this formula. Let us say that we have performed certain experiment and these are the possible outcome of that experiment, right? It can the outcome can be either 0, 1, 2 till 4. Okay, and fx is their corresponding probability. So the probability of experiment resulting 0 is 1 upon 5. The probability of experiment resulting 1 is 1 upon 5. Right? So what is an expected value of this experiment? Right? So for that, this formula we will be using. This is nothing but your random variable multiplied by its corresponding probability value, and we'll do the summation of over it. So here 0 multiplied by 1 upon 5 plus 1 multiplied by 1 upon 5, and likewise for the other term. The result is 2. Right? The expected value is 2. That means what? If I perform this experiment, on an average, I'm going to get 2 as my random variable. Right? Is it clear?
So when you say 2, on an average, you're going to get 2 means your output is most likely going to be 2. Is that what it means?
Output is not exactly 2. It is resulting to random variable 2. Now this 2 is the mapping, right? For example, the way we have mapped head with 0, tail with 1. So actually the output could be something else. But, you know, here, since we have represented that outcome with 2, that's why we are saying that on an average, it is going to give me random variable 2.
Okay. So giving random variable 2 means whatever mapping it is associated to, that will be the
yes
most likely output.
Yes.
Okay.
Okay. Now, so this was the basics about probability. Now we will quickly see some of the concepts coming from information theory. Okay, and I won't be able to cover the entire part of it, but I think one or two topics we can cover here. We'll start with the information content. Okay. So here also, let me give you an example. If I tell you a statement, if I say you that sun rises from the east, did I give you some meaningful information, some informative sentence I did I speak?
Yeah.
No, right? I did not give any meaningful sentence because the information there was 0. Everybody knows that sun rises from the east. There's no uncertainty.
I think it's the same thing, right? Didn't you say the same thing, that the sun rises from the east?
Yes. So here I made a statement, sun rises from the east. There is no information contained in it because everybody knows that sun rises from the east. There's no uncertainty involved here.
Okay.
Right. So see, the main point which I'm trying to make here is anything which is 100% certain, right, which is like a universal fact, that information, that sentence doesn't have information, that is not really meaningful because that is a universal fact. So the probability of occurrence of an event is inversely proportional to its information content. For example, if I would have said something like the probability that this stock X is going to hit its new high, right? Then this statement would have been a very important statement, right? This sentence carries a lot of information because there are a lot of uncertainties involved in this sentence, right? So information is inversely proportional to probability of occurrence of an event, right? Are you able to make an intuition? I'll repeat here.
Can you give one more example?
Yeah, let me give another example. Okay, if I say a sentence, right, or if I perform an experiment, if I have tossed a coin, and then I say that the probability of getting head is 0.5. right? Then what I'm saying is the information content of this claim is very low, because we know that the probability of getting head when we toss a coin is 0.5, right? Whereas
Okay.
if I say that tomorrow it's going to rain with a probability of 0.7, right? Then the information content of this sentence statement is high, because this is really an uncertain event.
Yeah.
Right? So what is happening here is, if the probability of occurrence of an event is high, is certain, then the information content is low. But if the probability of occurrence of that event is less, then the information content is high. Sorry, here it should be 1. This is inversely proportional, right? It is inversely proportional. Is it clear?
But why is it inversely proportional? Because the probability of occurrence of an event is directly proportional to the information, right?
No, it is inversely proportional, right? See, if the event is uncertain, if
Yeah.
that means what? Probability content is probability is less. If the event is certain, then definitely probability will be 1, right?
Yes.
If the event is uncertain, that means probability value is less. And if
Yes.
the event is uncertain, that means information content will be high,
Yes.
right? So that is why here this expression comes in. We'll elaborate this sentence tomorrow.